All right, so this is CT1 in a new chapter. And the basic idea of this lesson that you already heard in class, there's kind of two big ideas. One is the idea that when we apply a sequence of rigid motions that maps one figure onto another figure, we get two figures that are congruent. And so one, you need to know what is congruence, how do we define it, and then how do you write a rule for that sequence of rigid motions. Okay, so that's the idea. And so we're going to define congruence, and there's a real common phrase used with congruence, and often we say that two figures are congruent if they're the same shape and size. And that's true, but it's not necessarily a definition of what congruence is. We're going to use the idea of transformations or rigid motions to define congruence. And we're going to say that congruence is the mapping, remember that means moving of one shape, onto another through one or more isometric transformations. Remember, isometric transformations are those that are rigid motions. And so you can see that this triangle has been translated along this vector and then reflected over that line. And so what we have is a sequence of transformations that maps one triangle onto another through isometric transformations. Therefore, those two shapes have to be congruent because isometric transformations preserve distances and angles. So the distances and angles on this triangle must be the same as the distances and angles on that triangle. So we can say, because these are isometric transformations, we can say that triangle BCD is congruent to triangle, in this case, B double prime, C double prime, D double prime. Right? So that's our symbol for congruence. It's a similar and an equal sign. Similar meaning that the two triangles are proportionate. And equal saying not only are they proportionate, but all their sides and angles are equal in measure. Okay, so the triangles are congruent because triangle BCD is translated by vector, and we'll call it B prime, and then reflected onto triangle. Oh, I didn't put my double primes there. B double prime, C double prime, D double prime. Okay, so just another way to phrase it. Two figures are congruent if and only if one can be mapped onto the other by one or more rigid motions. And those rigid motions are rotations, reflections, and translations. Right, and this is just a recap from the last chapter on transformations. We know that rigid motions are those that preserve distances and angles. And when that gets applied to shapes and congruence, distances means essentially the size, and angles kind of refers to the shape. So we've got distances and angles are preserved, size and shape are preserved through rigid motions. All right, so then if two shapes are congruent, you need to be able to write a statement that says they are congruent, and that's just called a congruent statement. It relates one identical object to another by identifying the corresponding parts. Okay, so when you state that two figures are congruent, the order that you write the letters is important. So corresponding parts must be written in the same order. Because the order tells you which angles and which sides are congruent. So these two triangles are congruent. And we're going to just write a statement of congruence. We want to just make sure that we write the order to show that all the corresponding parts are congruent. So we can start by saying triangle, and it doesn't matter how we name this one, RKO, is congruent to. Well, now we need to make sure that we choose the corresponding angle to R. So notice R has one hash mark and D has one hash mark. So R corresponds to D. K has 2, M has 2, so K corresponds to M, and obviously E is left over. So that's a congruent statement. And I'm going to ask you on a quiz, write a congruent statement from this diagram. That's all I'm asking. Okay, and from that, we know which angles are congruent and which sides are congruent. So we can list the congruent angles. And that's angle R is congruent to angle D. Angle K is congruent to angle M. And we're doing this just based on the statement. We don't need a diagram to look at this, or to know this. Angle O is congruent to angle E. Okay, and likewise, we don't need the diagram to know which sides are congruent. This is representing side RK, and it's congruent to side DM. So we can write that RK is congruent to segment DM. KO is congruent to ME. And then for this last side, you could call it RO or OR. Doesn't matter. We'll say RO, as long as we name the second one in the same order. We started with R, so we have to start with D. DE. Okay, so this is the first you do question. Go ahead and write the congruent statement, list the congruent angles, and, oh, that's a typo. The congruent angles and the congruent sides. Okay, the focus of the chapter is on congruent triangles. And, we're just discussing what it means to be congruent for the most part in this section. But we can define what it means for two triangles to be congruent. And we'll say that two triangles are congruent if and only if corresponding pairs of angles and corresponding pairs of sides are congruent. Okay, that means same size and shape. Okay, and we can see that these two triangles are congruent. All the sides are congruent, all three sides, and then all three angles. And then one thing we're going to get into later on in this chapter is kind of the idea of what's the minimum amount of information we need to determine congruence. In other words, can we, let's say, if we didn't know these two angles are congruent, A and D, is that still enough information to know that those two triangles are congruent? Or do we need to know the angles at all? Or if we just know the angles, are the two triangles congruent? So that kind of information is where we're going. Right now, you just need to be able to look at a congruent statement and label a triangle correctly. Right, and so triangle BDC is congruent to triangle MLK. So we start with B, and what I usually do is, instead of marking 1 arc, 2 arc, 3 arcs, just because it's hard to do that in pen and make it look neat, is I just put, since this is my first angle, I mark it with 1 hash mark, right? So M is also going to have 1 hash mark. D is the second angle, 2 hash marks. L is the second angle, 2 hash marks. And then C gets 3. And K gets 3. I just find that to be a little bit neater. Okay, and then we also need to mark the sides. So BD and ML. So we can put 1 hash mark on BD, 1 hash mark on ML. DC and LK, they're going to get 2. Right, and so this last side, and notice the last side, it's between the 1 and the 3, and this one's between the 1 and the 3. So we know we've got the right corresponding pair. All right, so go ahead and mark this triangle to show that it's congruent. And right now, what I want you to do is mark everything. If you already know, what some of the minimum information is, at the moment, I just want you to write down everything. Okay, all corresponding sides and angles. Okay, so next, remember, we're defining congruence in terms of transformations. And so, if we can map one figure onto another through a sequence of rigid motions, then we know that those two figures are congruent. So right now, just saying, what is this transformation that maps triangle ABC onto triangle KLH? And right, we've got rotations, we've got reflections, we've got translations. And to me, it doesn't look like it's been flipped over because it's not lined up. But notice if you go from C to H, A to K, B to L, they all go through this single point. So what is that telling you? Well, it's telling you that it's been reflected, or no, sorry, excuse me. Well, it could be reflected through the point, but it's been rotated 180 degrees. So we'll write our rule here for that transformation. We're going to say it's a rotation about the origin of 180 degrees of triangle ABC. So we know, because of that rigid motion, that triangle ABC is congruent to, well, what's corresponding to A? That's K, corresponding to B is L, and then corresponding to C is H. Okay, so this is the transformation, that's the congruent statement. So we'll go ahead on this one, identify, whether this is a translation, a reflection, or a rotation. Write the rule, and then the congruent statement. Okay, so I've already mentioned this, that congruence means mapping through a sequence of transformations. Well, so far we've only talked about one, one reflection, one rotation. But it can be multiple transformations that gets you from the first figure to the last figure, the preimage to the image. Well, before we get into a sequence of transformations, let's talk about like a sequence of functions. All right, let's relate it back to algebra. In algebra, you learned about function composition. That was something like f of g of x. That's just notation. And that just means that the output to one function becomes the input for another, right? So it goes from one function right into another function. And so here are, in this example, two functions, f of x and g of x. One's linear, one's quadratic. And we need to find f of g of 2. Okay, and we discussed this in class, so hopefully it's familiar. But the idea is we're plugging the g of 2 into the f. So we need to evaluate g of 2 first before we put it into the f function. And so if you want to draw one of these little function machines, you can. I mean, I think they're helpful in terms of a diagram. But the first function we're going to apply is the g function, right? We're putting 2 into g. So this is our g function. We're putting 2 into it. And the rule says you square your input and add 1. Right? So if you square your input and add 1, out comes 5. But this output is now going to become the input to the f function. And so now we're going to drop 5 into a function. Right? So 5 goes into the f function. The f function rule says you multiply inputs by 3 and subtract 4. So 5 goes in. 3 times 5 is 15. Minus 4 gives you 11. So through this sequence of functions, when 2 goes in, 11 comes out. So we say that f of g of 2 is 11. Okay, so here I just want you to do f of g of negative 2. And you can follow the same format. Just negative 2 goes in, what comes out, and then write your final statement down here below. And before you start, just remember, it's important to notice that the innermost function is the one that you do first. You work from the inside out. So the innermost function is performed first, and the outermost function is performed last. Okay, so do this, and then we'll just talk about this question on page 7. All right, so lastly, this last example, we did one of these in class. So this one is a you-do question. You're going to do it. But this is the original relationship. Here's the preimage, here's the image, and the question says, are those two congruent? Okay, well, they are, and you want to be able to explain why. How do you know? This shows you how it got there, right? This image moved to here, and then it moved to there. I don't tell you how those moved, like what the rule was, but what I want you to do is write the rule in function notation to show that sequence of transformations. Right? And if you need an example, there is one on page 108 of the workbook. All right, so that's it. The big ideas for this, big ideas. Two figures in the plane are said to be congruent if there exists a composition of basic rigid motions that maps one figure onto the other. That's one big idea, what congruence means. And then the other big idea is just how to write the sequence of functions, a sequence of transformations using function notation. And that's what this example is. And we did one in class. So look back at that one to figure out how to do it. All right, that's it, and I'll see you next time.